Sample mean, sample mean. Everybody loves the sample mean. Oh, hi, I didn't see you there. Today we're going to talk about the Poisson distribution, another important discrete probability distribution. This has a relationship with the binomial distribution in a very specific way, and we'll talk about that after we just talk about the distribution in general. So, a Poisson distribution, discrete probability distribution, often arises as the number of as a distribution of the number of occurrences of an event in a given unit of time, area, space, volume, these kind of things, distance, and it has to follow some pretty specific conditions for it to be truly a Poisson. And in the reality and practical situations, almost always we'd be using it as only an approximation, but it can be a very, very useful approximation. So overall, we're going to think of it at times. One of the first little thoughts here is, can we think of events occurring randomly and independently through time or area, volume, distance, this sort of thing? And there's many different random variables that have been attempted to be modeled with the Poisson distribution many times. And depending on the specifics of the circumstances, might be a very good model, and other times it might not be so great. But let's say something like this, been used to model the number of calls arriving at a switchboard in a minute, let's say, or the number of chocolate chips in a cookie. Let's say the chips that you're getting, the cookies you're buying at the grocery store, and certain your favorite chocolate chip cookies or what have you. There's obviously some variability in the number of chocolate chips in there, and might try and model the number of chocolate chips in a cookie with a Poisson distribution. And here, the number of radioactive decays of a substance in a 1 second period, or just different unit of time. And that one, the number of radioactive decays, probably a lot of times Poisson provides a really, really good approximation to that distribution. But whether something actually has a Poisson distribution or not depends on the specifics of the situation, and there's a bunch of different ways of phrasing it and different ways we could talk about this, and I'm going to have it a little bit simplified here. So a couple of things. One big thing that we need, the occurrences of this thing, car accidents, if we're talking about those, or the earthquakes, or whatever it is you're modeling, the occurrences here have to be occurring independently in time. In other words, knowing when one happens, that doesn't give you any information about when another one will happen. So I'm going to phrase these things in terms of time a fair bit, but it's the same idea if we're talking about distance, length, volume, this sort of thing. So that's what we mean by independent in a casual sense. If we were writing this out formally mathematically, we could express this in certain ways. But in a casual sense, this gets to the heart of the matter. They're independent if knowing when one occurrence happens, when this event happens, it doesn't give us any idea about when the next one will happen or the one after that will happen. There's just no information about that. And then this part, which is a little bit overly simplified, but we often go with this to start with this because the real situation is a little bit more complicated, and we can't really have a full grasping of that until we understand the basics. So a lot of us start out with this, where we say, okay, another thing is the probability that an event occurs in a given length of time doesn't change through time. So that theoretical rate at which these things are happening stays constant through time. Now, purely technically speaking, we can have different scenarios arising that still give us a Poisson where we do have that rate changing. But for our purposes, for now, we'll go with this. And then usually we add on the other situations later. So this is a bit of a simplification. Mathematically, it doesn't have to be this way, but we usually start out with this and say that these are the conditions for our Poisson. Now, we are counting up the number of times this thing occurs, the number of occurrences we get. It'd be the number of earthquakes, the number of car accidents, the number of calls coming into that switchboard, the number of radioactive decays. We're counting those up. Okay, we're counting up the number of times that happens. And if our conditions are satisfied here, then the number of events in the fixed unit of time is going to have a Poisson distribution with this as the probability mass function. So this is what we would use to figure out our probabilities. So one thing to note always with these probability mass functions when we're talking about mathematical distributions, probability distributions, etc., in this case, our probability mass function, it's not complete until we say what values it can take on. So one thing to note here, we're counting up the number of occurrences in a given unit of time, area, length, this sort of thing. And so we can't get less than 0. So pretty natural that 0 is our lower bound. We could get 0 or 1 or 2. Wait a minute. The way this is phrased, there is no natural upper bound. There's no natural upper bound. There's no fixed thing like there is with the binomial where we're doing a fixed number of trials, where we're doing n trials, shooting 70 free throws. Let's say you can't make 87 free throws if you only shoot 70. So in the binomial, there was a fixed upper bound. In the Poisson, there's not, because we're counting up the number of times something happens in a fixed unit of time, say, and so there is no upper bound. So this just shoots off to infinity. There's infinite possible values your random variable can take on if it's a Poisson random variable. Now, you might say, well, how is this going to work in practice? Well, in practice, sure, you're not going to get a Googleplex of phone calls coming into to your switchboard in a 1 minute instant of time, or 1 minute unit of time, or an hour, or anything for that matter. But in practice, this is going to work out for us because the probabilities of these occurrences here, of these number of occurrences, can get very, very small and essentially like very, very near 0 as your values get higher and higher. So even if in a practical situation there's a bit of a natural upper limit, that's not a big deal. And once again, we're almost always going to be using this in scenarios where it's approximately the case and not perfectly theoretically this thing. Okay, so this is actually coming from a limiting version of the binomial distribution under a very specific thing that we'll talk a little bit about later, but this is our probability mass function. E is our regular E, base of natural logarithms, 2.71828 to 5 decimal places, but it has infinite decimal places there. It's an irrational number, one of our big numbers that come up a lot in our mathematical world. And the exclamation mark, of course, is factorial. It has one parameter, so a single parameter, lambda, and it so turns out that lambda is the mean. So the mean number of occurrences is lambda. That's what lambda represents, the mean number of occurrences. But it's also the case for a Poisson that's what the variance is as well. The variance is lambda. So for a Poisson random variable, your mean and your variance are the same. They are both equal to lambda. There's one parameter of the distribution. Okay, so we're going to use this to come up with probabilities for in various situations, but before we even attempt to do that, I'm going to just remind us of this situation. These events are occurring independently in time, and the probability an event occurs given a length of time doesn't change through time. So I'm going to try and help us visualize that a little bit. If we look at this situation, where we might think of this as a field with something in there, a rock or a certain type of flower or something like that, say, whatever. It's an area, and we have the dots representing occurrences of this thing. And I've set this up so that they are occurring randomly and independently. And in squares of this size, I've made it such, you wouldn't know this just by instantly looking, but I've made it such, I've created this such that they are occurring randomly and independently with a theoretical rate of about 1.4 per box. So if we randomly select a box, an area of this size, of the size of the box, then we're going to get a theoretical average of 1.4 instances in that box. And the conditions here of the Poisson are satisfied here. This would be a Poisson. This looks like a Poisson for this situation. If we're counting up the number of occurrences in a randomly selected area here, that's going to have a Poisson distribution. And I've created it like this. I've gone in, I've selected values, X and Y values independently as sort of a certain way, and done it in this fashion. And that's what it would look like when they're distributed randomly and independently throughout that entire area. Now let's look at a couple other possibilities. Here, we have a situation where there's some clumping together. They are not occurring independently of one another here. If you know where a dot is, you know that now it's more likely there's other dots around. There's some clumping occurring. And the one that always jumps into my mind here, even though there's all sorts of examples where this type of stuff happens, the one that jumps into my mind, cows in a pasture. Okay, you drive by cows in a pasture, they tend to group together. Of course, they might not. Of course, you get solo cows, etc., etc. But they do tend to group together. And so we might see something like this with cows in a big field where we have them grouping together. And so they're not occurring independently here. And because the cows like to group together, they have a tendency to do that. So those occurrences aren't occurring independently in a spot with the cows, and that results in them not Poisson. The number of occurrences in a little given in a randomly selected box is not going to be Poisson. What's going to happen here, if we contrast these two scenarios, is when they're clumping together, we're going to get a lot more big numbers. A lot better probability of getting a big number here than we did up top. And we have a lot better probability of getting a 0 because there's lots of empty space because they're clumping together. So in a situation where we've got this dependency and these clumping together, it's not going to follow the Poisson distribution. We're going to get too many zeros and too many big numbers. It's just has a different distribution. And conversely, what if, say, these things were spread apart evenly? So they're not, randomly and independently scattered about here. They are spaced absolutely evenly as I could make it. And so then if we randomly selected a square area like this, we're not going to get really big numbers, and we're not going to tend to get 0. We're going to tend to get 2 in there, right? Quite a bit, probably 2 or 1 almost all the time, depending on where we grab. And so there's not going to be the variability that we would see under the Poisson up here, where they're scattered randomly and independently. And there's more of just a separation effect. And so again, for sort of the opposite reason as for the cows together, this sort of situation would be not Poisson. And so one thing that jumps into my mind for this one would be, let's say, the lights in a huge parking lot, right? It would be something along these lines, distributed along the way in this uniform fashion. And then the number of lights in a randomly selected square would not have a Poisson distribution. So this is going to be a little bit hard to think about at times. That's just naturally for the Poisson. It's a little bit harder to think about than for a binomial or a hypergeometric or some of these other distributions that are pretty intuitive, I think. Poisson is a little bit trickier to think of, and it's a little bit of a gut feel, a little bit of shoulder shrug about whether it would be reasonable in a certain spot or not. Okay, so let's look at an example here. A certain volunteer fire department responds to an average of 7 emergencies per month. And I did a little digging. This is true of this is roughly true of a certain volunteer fire department that I did look up. So they're going to remain nameless here because I am simplifying the situation a little bit. But I did look one up and check into things. I think this is a pretty reasonable Poisson here. So suppose that the number of emergency responses in any given month follows a Poisson distribution with a lambda value of 7, a mean number of occurrences of 7. It's not going to be perfect. This would not be perfectly Poisson. And there's a number of reasons to think maybe there'd be some clumping together. One emergency leads to another emergency. Maybe there's an arsonist on the loose, right? They're starting fires all around town all of a sudden. If there were, they're not occurring independently of one another. Those fires that they're getting a call on, that sort of thing. So it wouldn't be perfectly Poisson, but I think for a rough approximation, I think it would be pretty reasonable. In any event, I'm saying let's suppose it's Poisson and do a calculation. So if we did this, say, remember our lambda is 7 in any given month, And the number of emergency responses if lambda is 7. There's some just a randomly selected month. Let's say if we work it out and we work out our probability mass function for our Poisson distribution, we're going to get these probabilities. So this is our probability mass function. And you'd see here there's 6 and 7, and here 6 and 7 are the most likely outcomes. You just see there's a little bit of right skewness in this particular case. The shape of the distribution is going to depend quite a bit on the value of lambda, but for a mean of 7, it looks something like this. If lambda's really close to 0, you're going to see a little bit more skewness, and when you have lambda getting bigger, well, you're going to have a bigger mean and larger variance, but it's also going to be sort of more bell-shaped as that happens as well. Okay, so let's see if we have this. So in a given month, let's say we just have a randomly selected month. Let's phrase it like that. The probability the department responds to exactly 10 emergencies. I want to the probability that my x equals 10, so I'm going to let x be a random variable representing the number of emergencies that they respond to. And I'm saying, suppose it's Poisson with a lambda of 7. That was the idea. Okay, so if we're just putting this through, well, it's lambda to the x, e to the minus lambda over x factorial. And our lambda is 7, and we want to know the probability x takes on the value 10. E to the minus 10, right? Because e to the minus 10. Don't do silly things like this. E to the minus lambda, e to the minus 7, e to the minus 7. Okay, e to the minus 7, it's e to the minus lambda. Lambda to the x, e to the minus lambda over x factorial. And so that is 10 factorial. Okay, so if we put this into our calculator, or with R has the dPoisson that'll calculate this for us, or we can just punch this stuff into our calculator, and we're going to get to 3 decimal places anyway, rounded to 3 decimal places, 0.071. 0.071. 0.071. That's what that works out to. And that is a probability we get exactly 10. And that, if we look here, this is 10 in my distribution, and that height there, that's the probability. That's what I just figured out, right? Or what we just figured out, the probability that x takes on the value 10. And we could do this for all the other possible values of our random variable, all the way from 0 on out towards infinity. So we couldn't do it for all of them because we'd be doing that for a little too long if we were trying to go to infinity, although the probabilities, as we can see, start to get pretty small out here and eventually get very, 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 very close to 0. So, of course, this couldn't be a perfect model for this situation. We know with certainty that this volunteer fire department is not going to respond to 100 trillion emergencies in a month, right? We know that. Now, the probability of 100 trillion is very, very small by the Poisson, but it's also impossible for this fire department, volunteer fire department, to respond to 100 trillion. It's just not happening. It's 0 probability. So Poisson can be often used in spots like this where could be thought of as a reasonable approximation, where these emergencies, let's say, are happening, to a rough approximation independently of one another. And we have this situation where the mean number of occurrences in the month is 7, so probably overall a pretty reasonable spot to use it. We'll discuss this sort of thing a little bit more down below once we get some more of these calculations out. So in a given month, let's say, what's the probability they respond to fewer than 3 emergencies? So same idea, right? It's a discrete random variable. Probability your random variable takes on a value less than 3. So fewer than 3, less than 3. What are the possible values of a random variable that are less than 3? 0, 1, and 2. And so we have to use the Poisson probability mass function on each one of those and add them up. Now, obviously, we don't want to do this, many of these things in our calculator. There's functions in statistical software that'll do this for us. Of course, we could calculate this either with dPoisson in R, getting us the probability of each individual value 0, 1, and 2 and add them up, or even faster, use Poisson, which gives us the value of the cumulative distribution function. Or in other words, if we put Poisson and figure this out, we're going to get directly the probability that x takes on a value less than or equal to 2. Okay, so just to visualize this, what happened, that's 0.0296, that's fairly low. That's these three probabilities, these three heights added up. And we can see, well, that makes sense, that's going to be pretty low. We had a mean number of occurrences of 7, so the probability of getting 2 or fewer, not too shocking that it's quite small. Okay, so that gives us an approximation in certain settings like this, and we might use this in a variety of different places. And might think of this in terms of number of car accidents on campus in a given week, number of earthquakes that occur in South America in a given year, things like this. And again, in many spots, it's not going to have truly a Poisson distribution, but it'll be a useful approximation. And like I keep going on about from time to time and repeat here and there, that's a large part of what statistics is about, coming up with mathematical and probability models that are not actually true, don't perfectly reflect reality, but are a useful simplification of reality for us. Now, there is a very important relationship here which can help us visualize whether something might have a Poisson distribution or not. So this is a very important thing. There's a very important relationship between the binomial distribution and the Poisson distribution. So if we started out with this binomial probability mass function, say, we started out with our binomial probability mass function, if you remember, like our binomial n choose x, p to the x, 1 minus p to the n minus x. If we start out with that, and we let n go to infinity, and we let lambda equal np, just this thing, and we let n go to infinity, which is going to result in p going to 0, right? If we have lambda equaling np, that's staying constant. So I was kind of jumbling that all around, but we're going to let the lambda equals np, and then we're going to say, okay, n's shooting off to infinity while np's staying constant here. P's got to go to 0. It's the only way that can happen. And then in the limit as that happens, this goes to the Poisson. Okay, this thing, I'm not going to show you exactly, but this actually does go to lambda to the x, e to the minus lambda over x factorial in the limit. Okay, I have a video going through the mathematical details of that. But that's not quite so important, the limiting value in that as the general idea that, what's an implication of that really? That Poisson distribution can be used as an approximation to the binomial distribution if in spots where we have n is large and p is small. So when n is large and p is small, that notion, they say, hey, wait, is n shooting to infinity and p is going to 0 in that way such that our np stays constant? The binomial in the end becomes the Poisson. And so Poisson can provide this useful approximation at times. So let's just do a calculation to verify and talk about that a little bit. Okay, so cystic fibrosis, genetic disorder, causes thick mucus in the lungs and other organs, and approximately 1 in every 2,500 Caucasian babies is born with cystic fibrosis. All right, so let's say we have a random sample of 500 Caucasian babies, and we want to know the probability that exactly 2 have cystic fibrosis. This is a binomial problem. Okay, this is a binomial problem. If we randomly sample a Caucasian baby, there's a 1 in 2,500 chance that it's got CF. And if we're doing this random and independent sampling, then knowing what happens on one baby, whether they have CF or not, tells us, no information about whether another one does. So on the next one sampled, that sort of thing. So our binomial is perfectly satisfied here, really, right? It's a binomial with n is 500, and p is the probability that any one individual baby has it, and that's 1 in 2,500 if we're sampling Caucasian babies. And so this gives us the real probability. Probability x equals 2 through the binomial. That is through the binomial. It gets us, and that's our probability, 0.01635. That's our probability. That's fine, right? There, that's our answer, done. But we could use the Poisson approximation. So, and the reason we can use the Poisson approximation is we have a fairly large n here, right? We're doing this 500 Caucasian babies and a pretty small p, 1 in 2,500. So we have this situation where Poisson approximation is probably pretty reasonable here. If we did it the Poisson way, the Poisson approximation to the binomial, then we'd say, okay, what do we have? Lambda to the x. Well, we're going to need our lambda here, and we say that lambda is n times p, and that's 500 times 1 in 2,500. And I think we can do that one pretty well here, right? That's 1 in 5, or 0.2. So when we're doing this for the Poisson, we could say lambda is 0.2. The average number of babies with CF is going to be 1 in 5, because 500 of them, and 1 in 2,500, any individual one has it. And so we have lambda 0.2 to the x, probability exactly to have it, 0.2 to the 2, e to the minus lambda, so e to the minus 0.2 over x factorial, or 2 factorial in this case. So lambda to the x, e to the minus lambda over 2 factorial, right? Or x factorial there. And if we were to do that, we get 0.01637. Really close. Okay, really close. Okay, so what does that do for us? So first of all, we verified in this particular scenario, at least for this large n and that small p, that this approximation does work, pretty well. And as one rough guideline has it, like our guideline here, rough guideline, not a strict rule. The approximation is reasonable, just reasonable if n's bigger than 50 and NP is less than 5. That's just one guideline that people have here, okay? So it's not just not the be-all and end-all, and I'm sure there's different guidelines out there, but this sort of idea, if we start having a larger sample size and a smaller p, in this case we've got an n of 500 and a p of is very, very small here, so not a surprise that they were really, really close. So this guideline saying, okay, probably pretty reasonable in this situation. And we got an approximate probability that's very, very close by most standards to the true one. Now you might say, very reasonably, why do we care? Why don't we just do the binomial? Right? Well, there's a few things. There's a couple of main things here. One, we do have these some of these very large factorials in the binomial, or 500 factorial. If we're doing a really large n, then eventually, these things get to be huge numbers and can crap out. More so than in the Poisson here, which also has a factorial, but that's the x value. So depends on what we're doing. But that choose function of the binomial could be problematic at times, depending on our specific values. Especially when n gets very, very large, this could become problematic. But more so than that, I think conceptually what happens is there's certain settings where we can think of the underlying scenario as having a very large n with a very small p, right, of something happening. But we don't know the n and we don't know the p, but we might have a good guess as to the mean. And the Poisson only has that mean as its parameter. So if we had a situation like that, for instance, let's say we're talking about those radioactive decays, okay? A certain substance with a certain that's decaying. It has a certain number of uranium atoms, say, that are decaying at a certain small rate, suppose. Not happening very often. And if we were wondering about the number of radioactive decays in a certain amount of time, well, we don't know how many atoms we have, and we might not know the actual probability of any one individual atom having a radioactive decay. But overall, if we've got a Geiger counter or something, we might have some idea of the average number of decays. And then we couldn't use a binomial because we don't know n and p. But the situation is like a binomial with a huge N and a small p, and so Poisson should be working pretty well and a pretty reasonable approximation. And so then if we have an estimate of the mean, we can use the Poisson. Well, we couldn't really use the binomial. And so that can happen in real-world situations. That would not be uncommon, where we might have an idea of the average number of accidents at a corner in a certain amount of time, say, car accidents. But we don't, there's a lot of cars and everyone's a probability of an accident, and maybe it's not perfectly Poisson, but we can kind of loosely think of it as a situation where there's a large number of cars and there's some chance each one of them gets into an accident. And if we had some estimate of the mean, perhaps from prior data, maybe the Poisson model could be used pretty well, even though in reality it's not quite true. So when you're thinking about whether something has the Poisson distribution, one way to think of it is this binomial idea. Is it really in reality? Can we visualize this as a binomial with a huge N and a small p? And that's sort of a common thought where we can think about in our brains there. Okay, and so I'm going to look at just another example here, because it is a little bit tricky with the Poisson. I have a dedicated video to Poisson or not, right? When does a random variable have a Poisson distribution, where I get into this in a little bit more detail. But for here, I'd like to look at this one thing. This is inspired by a question I saw in a textbook many years ago, where somebody, they phrased it, they said, okay, suppose the number of fatalities in these plane crashes has a Poisson with mean whatever, and then asked a question asking for probabilities of a certain number of fatalities. Well, one thing here, what I'm getting at here, is the number of fatalities, the number of deaths in these plane crashes is not going to have a Poisson distribution, whereas the number of crashes themselves, that might be pretty reasonably approximated by a Poisson. I'm going to discuss that here. So here we have this situation where this is data from 1982 through 2023 from the NTSB, Part 121, so air carriers, and these were the number of accident, or number of what their term, NTSB accidents, how they phrase it, how they classify it, NTSB accidents in which there was at least one passenger fatality. That's what that's representing. So here, the number of these, we can think of them as plane crashes. Some of them were more minor accidents, but there were accidents with these planes causing at least one fatality. And then over here we have the number of fatalities, the number of people that died in those accidents each year. Probably not too unreasonable to think that the number of accidents in any given year, any sort of unit of time that we're going through, would approximately follow a Poisson distribution. Pretty reasonable to think of it this way, I think. Pretty reasonable to think that to a rough approximation, these accidents are occurring randomly and independently of one another. There's not a dependence there, right? There's independently. Knowing there's an accident doesn't give you information about when there's going to be another one. Typically, we can think of situations where there might be a tie-in, more on that in a second, but overall, the general idea is to think of those as occurring independently of one another is not outrageous, not an outrageous thought. Now, it would be tough to come up with the value of lambda, because safety's gotten a lot better, even through the last number of years. We can see, just sort of eyeballing this, that it looks like those number of accidents is down quite a bit, right? It's going just to maybe a bit of that is luck, but certainly at least some of it, technological advances and just a lot of work into safety of aircraft, including the hard work that the folks at the NTSB do. So, it would be hard to say precisely, in fact, impossible to say precisely what the actual value of lambda would be in any one instance. We got safeties getting better. We got more planes in the sky. But overall, we could say, wait, rough approximation here, being a binomial, sounds reasonable. We got tons of planes in there. We could think that tons of planes flying in the air. And each one of them has this tiny chance of getting into a fatal accident. And so, hey, wait, this is starting to add up to be kind of like a binomial with a huge N and a small p, leading us to the Poisson. The number of fatalities, not at all, because these are not occurring independently of one another. I do like to say this. I probably said this in the other video, right? But if you're on a plane, if you're getting on a plane, you're on the runway, and you heard that there was another plane crash that day, that's not really all that bad news for you, right? It's just not. That's not a terrible. It really doesn't change your chances very much at all of anything bad happening to you that day. If you're in that plane and you know the person next to you is dying in a plane crash that day, this is horrible news for you, right? So this is very, very, very bad news for you. These fatalities tend to group together. There's a lot of people in a plane. Sometimes plane crashes are not. Sometimes they're fairly minor, say, but sometimes it's the whole plane going down and everybody dies. And so we're having these groupings of deaths. And so we have these accidents, I think, roughly following a Poisson distribution, pretty reasonable. But the number of deaths, definitely not. Like we have all sorts of years with zero. No deaths, no deaths, no deaths. Lots of years with zero. There's a couple with one here in 2018, 2019. But like there's there's one death for each one of those accidents. But we have lots of years with actual zeros there, with no passengers dying in airline accidents, and then some years with huge numbers, these huge spikes to over 400, and certain plane accidents with several hundred people dying in one plane accident, and that sort of thing. So the number of fatalities would definitely not have a Poisson distribution. A Poisson distribution would not be a reasonable approximation, whereas the number of accidents themselves, or we could think of it, let's say, as the number of crashes, that roughly would have a Poisson approximation. Although, once again, it's just going to be an approximation. There's lots of settings, and including right here, where we could think, well, maybe there's a bit of a dependence there. Maybe one of these planes that they just made has a fundamental flaw, and that if something goes down, maybe that's pointing to there being an actual problem with some of the technology that might make it more likely that a similar plane goes down. That's one way, or we have the rather dramatic events of a 9/11, right? And so that 2001 and the very unfortunate happenings of that day, that several planes went down for essentially the same reason as part of the coordinated attack that day. And so those weren't happening independently. And so even something like plane crashes where we might think, oh, in general, right, probably, overall, roughly occurring independently of one another, the reality is very likely that there's some sort of dependencies there, whether it be sort of a subtle thing about design of aircraft or a more dramatic thing about terrorist attack. There often is spots where there wouldn't be this true independence, wouldn't be a true Poisson distribution, but still we could use things as approximately so. And very useful model for things like that. A very useful model in the probability world. It comes up a lot in various settings, but that's it for now.